Hi everyone, thank you so much for coming. Today is the fourth lecture in network security. So today we will have some mathematical again background, very important to know a little bit about algebraic structures, all right? Next week actually we're going to talk about the first algorithm, real algorithm that we use in real life. But for that to be able to understand it, we have to go through many stuff as you have seen. So these are the objectives. So we're going to talk about algebraic structures. So we're going to talk about the groups, we're going to talk about rings, and we will talk about fields. Maybe some of you have seen these terms in some of the algebra classes, but you know, we'll give you a nice introduction today, and hopefully that you'll see it useful. So as we know, cryptography requires sets of integers and specific operations. So we have integers and operations, all right? And we call them binary operations. Binary means there is one element, and there is an operation. So addition is a binary operation. Multiplication is a binary operation, right? All right, so we need to know how to combine these operations with the elements to create something called algebraic structure. So in this chapter, we'll define the three common algebraic structures.
The attendance, it's 577 that's on it.
I think this is a network security.
No, I've already signed it.
Just sign it. Find your name and sign it. Right. So the common algebraic structure we're going to talk about today: groups, rings, and fields. Groups and rings and fields. All right. So let's start with the groups, the most simple one. So a group is a set of elements with a binary operation. Binary, we mean with binary one more time, that it has left and right. It has two sides that it does the operation on. Binary here means two elements. We're not talking like a binary and decimal. No, that's not what we're talking about. Binary means it has two sides. So the properties that we have to have are closure, we'll explain it in a second, associativity, and commutativity, and existence of identity, and existence of inverse. How many? 5 conditions, right? So let's take a look at this group in here. All right, so we have a set, has elements. The elements could be integers, could be digits, could be letters, it could be elements, okay? Like for example, in here the set has A, B, C. This is a set. The operation is this circle. This black circle is the operation. And the conditions is closure, associativity, commutativity, existence of identity, and existence of inverse. So we have to note that the third property, which is in here, commutativity, needs to be satisfied only for commutative groups. So if you don't have this, the number 3, we still call it a group, but we don't call it commutative group. So we have group and we have commutative group. All right? Are you aware with that? All right. What are the applications used for groups? Involves a single operation, binary operation, addition, multiplication, subtraction is an operation. The properties imposed on the operation allow the use of the pair of operations as long as they are inverse of each other. Let's take an example. Okay, so this example in here, there is a set of Zn, regardless of what n, and the operation is, the binary operation is the addition operator. The addition operator. So is this a commutative group? Is it a commutative group? We have to test it, right? We have to testify the define condition. Okay, so we can perform addition and subtraction on the elements of this set without moving out of the set. So let's take another example in here. What is this? This is a set of elements in N that have multiplicative inverse. Multiplicative inverse. So we have multiplication, and that's the set. Okay, it's an Albanian group. Let's take a look at this group G, which has a set of elements. It has only four elements in the set. What are the four elements? A, B, C, D. Fair? And has one binary operation. What is a binary operation? This circle. We don't know what it is. It's an operation. So let's check if this is a group. First of all, okay. So closure. What does it mean, a closure? That means the output of the operation is part of the set. So whenever we do any operation in two elements in here, it will get element in the same group, right? So you cannot find, for example, X and Y and Z, right? So when you look here, A operation with A gave you A. A operation with B gave you B. A operate. So do you see any element as a result in here out of the group set? No. So we satisfy the first condition, which is closure, right? What is the second condition? Associativity. So if you do the operation in the three elements, okay, in the three elements, so for example, if I do it, okay, if I do okay, A, the operation, B, the operation, C will equal to, okay, A, the operation with B, okay, with the operation with C. Right? Because you try it in the table, you'll find it getting satisfied. Right? Okay. Let's take a look about the identity. What is the definition of identity? If you multiply the element with the identity, will give you itself. So what is the identity in this table? What is the identity element in this table? A, right? Yeah. Who said A? Why? Because with A it will give you A. So you multiply it with A, gave you A, with A gave you A, B with A gave you B, C with A gave you C, D with A gave you D. So what is the identity? Is A. Okay, how about the inverse? Okay, what does it mean, inverse? If you multiply the element with its inverse, will give you the identity. So in here, what is the identity for A? A, because multiply A with A gave you A. What is the identity for D? Is B. So B multiplied with D gave you A. What is the identity for C? C. What is the identity for B? D. If you try it in here also, B with D gave you A, right? Alright, so we have the identity. So all the conditions are there, okay? Alright, so you could look at it, you know, okay. So for example, okay, let's take a look, for example, at here. Let's take a look at G. Okay, of Zn and plus. Okay, this is a group, or usually we write it like this. Okay, so let's look at the parameters. Okay, so what is Zn? Numbers, which is 0, 2, 1, 2, 3, 2, and minus 1, right? Right? So let's take a look at the closure. If you do the operation, 1 plus 2 gives you 3. 3 plus 4 gives you 7. So the closure is there because any element you'll have, so the condition number 1 is there in the closure. The second condition is the associativity, which is I told you, for example, so this is, let me put 1 here. Number 2, associativity. So 1, okay, so let's take a look, for example, 4 plus 3 plus 2 equals how much? 9. How about if you say 4 plus 3 plus 2 equals 9? Okay, so the condition is there. Then after that, you talk about commutativity, which is 3. 2 plus 3 equals 3 plus 2, which equals 5. Alright? How about the identity? What's the identity here? Anything you add it to the identity gives you itself. What was the identity? 0. Okay? So number 4, the identity 0 is the identity, right? Number 5 is the inverse. What is the inverse of any number? It's negative, right? The inverse of any number is it's negative. So the inverse of 3 is -3, and so forth. So what we call this in here, commutative group. Commutative group, right? That's good. All right. So I think the idea is clear for all of you. Let's take one more example in here, which is a very interesting group. The permutation group. Okay. The set of all permutation and operation is composition, applying one permutation after the other. So what we have, this is the operation, the open O, and this is the permutation. So whatever input you have, okay, you're gonna go to the second, and so you know what happens in here. Whatever input in here, okay, whatever input in here will go to here. The input in here gonna go here. In here gonna go. That's a box, right? Like a box that switch from one side to one side, right? Okay, so if you do the operation in here, okay, you'll see that that's the output. So for example, if you put, for example, the input 3, 1, 2, okay, so 3 gonna go in here, right? Gonna go here, then gonna go here, gonna go here. So 3 goes where? 3 goes where? To that. So the first input will go where? To the third. So that's why we have 3. The second input goes where? Here, here, here. Second becomes second. So second continue to be second. How about the third? You go here to here to here. Becomes first. First. All right. So this is like a composition, a process. So this operated with this will give you this output. All right. So in here, what we are talking about, binary what operation. It's not necessarily to be operation that we know, like multiplication or addition or subtraction. It could be any operation. All right. And you're talking about the group. It's not necessarily to be a group of digits. It could be group of anything. So you could here, for example, if the member of the group could be apple, banana, orange, could be anything, right? So you're performing an operation, all right? So I think you understand where we're going to. We are going to how to use this to blend the data, mix the data, right, with these operations, okay? So look in here, that's the operation table for permutation group. So this is 1, 2, 3. If you do the same process here, right in here, you see, okay, it gives you a result, and so on and so forth. So what you notice in here, Okay, what are these? The inverse. This is the inverse. Okay? Let me ask you, where is the identity? Look at it, tell me where is the identity element. 1, 2, 3. Why? Because remained, did not change, did not change, did not change, did not change, did not change. So where is the identity? It's 1, 2, 3. Okay? Where is the inverse, for example, 2, 3, 1, 2? 2, 3, 1. And so on and so forth. Clear? So I think it's a clear process to understand. Okay? Alright. So in the previous example, we showed that a set of permutations with the composition operation is a group. This implies that using two permutations, one after another, cannot strengthen the security. Cannot strengthen the security. Why? It's good to bring you to the same group. And so let's say you do composition, and then another composition, another composition. All the time the output will be one. It's a group, closed group. It will be one of the results. You're not changing, right? So, oh, I'm sorry. So it will not. This implies that using two permutations, one after another, cannot strengthen the security of the cipher, because we can always find a permutation that can do the same job because of the closure property. Because of the closure property. Alright? Okay. So there is something called finite group. Then we're going to talk about the order of the group, and then we'll talk about subgroups. Alright? So what is finite group? What is a finite group? You know, we call the group finite if it has a finite set of elements. So if the elements, for example, from 0 to n-1 to n-1, it's finite, because the number of elements are finite. If the number of elements in the set not finite, then it's not finite group. As simple as that, right? So if you look in here, for example, the group HZ10 plus, is this a finite group? What are the sets from 0 to 9? So it's a finite set, then it's a finite group. Okay. So what is a subgroup? Subgroup is when the set of the group is a subset of the other group. So, question in here. Is this H a subgroup of the group G? Yes. Who says yes? Who says no? How about you? You're not sure? Is this a subgroup of this? Yes. 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 All of you, yes? No. Because this is modulo what? What's the modulus in here? 10. What's the modulus in here? 12. So they are completely different groups. Yes, the subset of this, but this group is not subgroup of this, because the operation is different. The operation, this is modulus 10, this is modulus 12. So you have to pay attention for that. Right? So the answer is no. It's here. Alright. The answer is no. Although H is a subset of G, the operations defined for those two groups are different. This is modulus 10, modulus 12. The operation in H is addition modulus 10. The other one is modulus 12. Alright? Alright. Interesting, right? Okay. So let's talk about subgroups. So let's talk about cyclic subgroups. Cyclic subgroups that the operation repeats. Okay? So when we say, for example, A to the power n, that means it will repeat how many times? N times. So this will be A, operation A, n times. So in a subgroup of a group can be generated using the power of the element. So in the subgroup, okay, what's the first condition for a group? Closure. So if you do 1 million times in 1 million, the result always would be part of the set. Right? So in here, if you do it 2 times or 3 times or 4 times or 20 times, the result will be part of the, okay, so we have to understand. So cyclic subgroup, just you could generate more elements by repeating the operation, but no matter what you do, the result has to be part of the set. Part of the set. Agree? Okay, good. Alright, so let's watch how we can generate subgroups. Alright? So 4 cyclic subgroups can be made from this. So what are the elements for this? 0 to 5. What is the operation? And modulus? 6. So there is 2 groups, subgroups we know. So the group that has only the identity and the group that has all the elements. They are considered subgroups. So how many? These are 2. So each one has one element which is 0. What is 0? The identity element. So and there is also H4 which has the whole G. So it's a subgroup. Let's find another groups. So you'll have also H2 which has 0, 2, 4. And H3 which has 0, 3. So how many total subgroups we have in here? 1, 2, 3, 4. Let's see how we can generate the subgroups by the repeated operation, right? So always here, for example, when you say 0 to the identity, mod 6 always give you 0. So the operation repeated to the identity equals 0, right? So this is the first subgroup, which is H1. If you do it now, if you say 1 to power 0 will give you 0. 2 to power 0 give you 0. 5 to power 0 give you 0. There is no point, right? So this repetition will give you only one result, which is 0, which forms one subgroup, cyclic group. Let's take a look at the second one. So now 1 to power 0, anything power to the identity will give you 0. 1 to power 1 mod 6, how much? 1. So again, what's the operation in here? Addition. So that means 1. 1 mod 6 give you how much? 1. Okay, let's take a look. 1 to power 1 will give you what? I'm sorry, 1 to power 2 give you what? 2. Because what does it mean? 1 plus 1 will be the operation. So 2 mod 6 how much? 2. Okay, 1 to power 3 what does it mean? 1 plus 1 plus 1 3 times give you 3. How about 4? Will give you 4. 5 will give you 5. So this subgroup, cyclic group, generated what? 0 to 5, which is what? Which group? Group 4, the whole G. Let's go to the next element. What is the next element? 2. 2 to power 0 gives you 0. 2 to power 1 give you 2. I mean, to power, I mean, it's not correct word. I mean, you know, repeated once. We say operation. So in here, I mean, the best thing to say, 2 operation repeated twice. So 2 plus 2, 4. Let's go with the 3. Let's go 3. 2 to power 3. 2 plus 2 plus 2, 6. 6 and what 6 give you how much? 0. Repeated. Let's go with 4. 2 plus 2 plus 2 plus 2 how much? 8. Mod 6 will give you how much? 2. Repeated. So no point to keep going because it's gonna repeat the whole 3 digits. So this group, what does it have? 0, 2, 4. Which group is this? H2. Let's try to generate from here from 3. So 3 to 0 give you 0. 3 to 1, 3. So this generated 0, 3, which give you group 3. Okay, how about 4? Give you 0, 4, 2, which is group what? H2. So the 4 generated H2 and the 2 generated also H2. Still the same group, right? How about the 5? Generated the whole G. So you could generate the whole G from the 5 and from the 1. Okay? So you understand what is cyclic group. Cyclic keep, repeats, repeat, okay? Okay. So from this operation, how many subgroups we have, cyclic subgroups? 4. H1, H2, H2, H4, right? What do you notice about these subgroups? Do you notice anything? All right. So, 3 cyclic subgroups can be made from the group Z10. You know, the members that have inverse, right? With the multiplication. So, what are the elements of this group? 1, 3, 7, 9. We have learned it from previous lecture, right? Only 4 elements, not 10. Only 4 elements. So 1 and 3 and 7, they have multiplicative inverse. So the cyclic subgroups are 1 and 1, actually 3, the H1, the H2, the H3, okay? We said there is 2 groups always there. The group that includes the identity. What is the identity here? 1. So that's one group. And the group that includes the full group, which is G. And we generated this. We did the same process, you could try it out. The same process. But remember what we are doing here? Multiplication. So for example, 3, okay, mod 10, 3. Here, 3 times 3, 9. Okay, mod 10 give you 9. Okay, 3 times 3 times 3, 21. Mod 10, 27, I'm sorry. 3 times 27. 27 mod 10, give you 7, and so on and so forth. Okay, so again, remember the 3 things in here. Remember that in here, the power means repeated operation. Remember that we're using a modulus, and remember that we're trying to generate subgroups, and we see actually 3 groups in here. So 1, 2, 3, 1, 2, 3. These are similar. These are similar groups, right? All right. So in the cyclic group is a group that it is its own cyclic group. Okay, a cyclic group is a group that its own cyclic group. Okay, so E starts with the identity element, right? E is identity element, G squared, G n minus whatever, G n equals E. All right. So, so 3 cyclic subgroups can be made from a group Z10. We already saw these. The group G, Z6 plus, is a cyclic group with 2 generators. What are the 2 generators? 1 and 5. Why we call them generators? So the generator generates the whole group. Let's go back. So which ones generate the whole group? 1 and 5. What we call 1? A generator member. What we call 5? A generator member. Why? Because it has generated the whole group, the whole set. Okay, clear? Yeah. In here, which one is a generator? 3 and 7. Why? It has generated the whole group. So that's what, remember I asked you, anyways. So in here, the 3 and 7 are generators. You agree? All right. So Lagrange theorem. Lagrange theorem. What it says? It says, assume that G is a group. Clear? A group. What is a group? It has 5 conditions and has finite set of elements, right? And H is a subgroup of G. If the order of G, okay, what is, okay, we will not explain what's the order. What's the order means? The number of elements. So if you go to this in here, what's the order of this? 6. 6 elements, right? What's the order of this? 4 elements. 4 elements, right? That's the order. All right. So it says that if you have a G group and H group, and H is a subgroup of G, okay? If the order of G and G are, that's the order. That's how we write the order, right? So the order of G, you put 2 lines, equals how much? 6, for example, and H whatever, respectively. Then based on this theorem, H must divide G. H must divide G. Let's go back to our example. So, okay, so what is the order of here? What's the order here? 2. What's the order of G? 4. 2 divides 4. 4 divides 4. 1 divides 4. So if I give you a huge, I mean these are smaller groups, if I give you a huge set, a huge group, and I ask you look for subgroups, what you have the first thing to know? The size of the subgroups must divide the bigger group. Right? Must the original group. Alright? So let's take a look at another one in here. So for example, here, what's the size of the group in here? 6, right? 2 divides 6. 3 divides 6. 1 divides 6. 6 divides 6. Okay? So we already explained what is the order of the element. The order of an element is the order of the cyclic group it generates. The order of cyclic group it generates. Okay? Right? So what is the order, for example, of 7? It generates a group, has how many elements? 4. So what's the order of the element 7? 4. Alright. What's the element of 9? 2. And so on and so forth. Okay? Well, thank you so much. Everybody's awake today. So that's very good. Including the cameraman. We have to ask him some questions, right? Alright. So, in the group G equals to Z6 addition, the orders of the elements are, order of 0 is 1, order of 1 is 6, order of 2 is 3. Why is it 3? Because this will generate a group of 3 elements, and so on and so forth. Clear? Alright, we finished fields. Now you get certification. You know fields, enough fields. We're going to go to ring. What is ring? So ring has 2 elements, not only 2 binary operations, not one binary operation. Is an algebraic structure with 2 operations. Okay, 2 operations. The first operation here, it has the 5 conditions. So we have the set, one set, the same set. We apply the first operation, then the second operation. What are the conditions for the first operation? Closure, associativity, commutativity, existence of identity, existence of inverse. Simple. For the second part, it has only closure, that means the output has to be here. Associativity and commutativity. The third property is only satisfied for a commutative ring. So if it's what's the ring? If this is commutative, then we look for commutative. Remember, for rings, we spoke about ring. Has how many conditions? 4. We have commutative ring. Fields. Okay, the field, right? The groups. Group. Okay, the group. When you say group, has how many conditions? 4. The commutative group has how many conditions? 5. Remember this number 3 only for commutative group, right? Right? Yes. Then here what you have, commutative ring. So this has to be commutative, this has to be commutative. And the operations is dark circle and white square, right? Y square. All right. So the set Z with two operations, addition and multiplication, is a commutative ring. We showed that R, which is ring, for Z, okay, plus and X. So the first operation is addition, then multiplication, and this satisfies all of the 5 properties. You could try it out, right? You could try it out yourself. You'll see it will satisfy the whole process, right? Okay. All right. So now we're gonna go to the field. The field the same as ring, but the first one has the 5 conditions, and the second operation has the 5 conditions. The 5 conditions, except for the existence of inverse, the identity element of the first operation has no inverse with respect to the second operation. So the identity element, all the elements has inverse except what? The identity. So let's take example. If this is addition and this multiplication, what is the identity for addition? 0. Right? For addition, the identity is 0. The 0 in here does not have a multiplicative inverse. That's it. So let's repeat one more time. Field, same as ring. It has all the 5 conditions in here and here, except one element in here does not have inverse, which is the identity in this operation. Good? That's it. Okay, so we're gonna come, when you look at finite fields, Galois showed that for a field to be finite, the number of elements should be p to power n. What is p? It's a prime number, and n is a positive integer. So what he says that for a group, for a field to be finite, it has the number of elements has to be some prime to power and a positive integer. Primes like what? 2, 3, 7, 5, the prime numbers. What's a prime? Is a number that could divide by itself and 1. All right. So that's what is, that's what. So when you look in here, for example, Galois field of prime, of course, to power 1 in here, which is a prime, which is a positive number. Okay. When n equals 1, we have the field of P. This field can be the set of 0, 1 to P minus 1. So Z of P to be 0, 1 to the prime minus 1 with 2 arithmetic operations. So let's take a look in here. A very common field in this category is of 2. 2 is a prime, right? 2 is a prime, right? So what are the numbers? Will be 0 and 1, right? The field is 0 and 1. That's a set, 0 and 1. Okay? And 2 operations. What are the operations? Addition and multiplication. So this is the group, which is 0 and 1. Okay? This is the field of 2 elements. And the operations, addition and multiplication. So what will happen in here? 0, 1, 0, 1. Okay, if you do the addition, that's what will be the output. So you have the 5 conditions: the closure, the associativity, the commutativity, the existence of inverse, and the identity, right? And we look in here, what is this? The multiplication. You multiply them, it has the 5 operation. Except, okay, the identity in here does not have inverse. So for example, what's the identity in here? 0. Does not have inverse. Okay. But for additive inverse, 0 has 1 and 1 has 0. What is the multiplicative inverse for 1? 1. What is the multiplicative inverse for 0? None. Okay. So did we satisfy all the conditions for a field? Yes. Okay. So we can define How much time I have? 15 minutes? Okay. Of 5. So is 5 a prime? Is 5 a prime?
Yes.
Yeah. What are the elements? 0, 2,
3, 4.
2, 4, right? So Z5 is a prime with addition and multiplication. So this is a set. These are the multiplications. So you could do the operation. You could do the operation. Additive. All of them have additive inverse, but 0 does not have multiplicative inverse. Any other ones have multiplicative inverse. Okay. You want to try one? So 4. 4 times 4, how much? 16. Modulo 6, how much? Modulo how much? 5. How much? 1. 1 is the identity element, right? Correct? So you can verify all of that, alright? Alright, so summary in here, algebraic structures, we have a group, ring, field. So supported typical operations, addition, multiplication, or division, multiplication, addition, subtraction, division, and the multiplication. Okay, supported typical sets. Okay, the multiplicative inverse of n or n. Okay, ring. Okay, Z and field usually work with prime. You're looking for a prime number, like Galois fields. Okay. All right. So we started nicely. We started with group, ring, field, and then after that we went from field to Galois field. Galois field. We explained field of a prime number. Now we're gonna talk about a field of a prime to power n. Fair? Fair? To power n. So, and that will bring us to polynomials. All right? So, a cryptography, in cryptography we often need to use 4 operations, right? In other words, we need to use fields. We can work in GF of 2 to power n. So 2 is a prime n, and uses a set of 2 to power n elements. Set of 2 to power n elements. The element in this set are n-bit words. N-bit words, right? So to write any number which is 2 to power n, how can you represent it in a binary? In n bits, right? So if I say 2 to power 3, okay, what is 2 to power 3? How much? 8. How many bits you need to represent 8? 3 bits, right? So trying to represent it with a binary, right? Okay. So let's take this is very important in cryptography. I mean, we started to come to this point. We went through smoothly to come to this point. So let's talk about polynomials using a generator, and then we summarize it. Okay. So look. Okay. Let us define GF 2 to power 2. So there is a condition for GF. The lower number has to be prime. In this case, it's what? 2. 2 power 2. Field in which the set has 4 2-bit words. Why 4 2-bit words? Because how many numbers we could generate? 2 to 0, 1, 2, 3. How many bits you need to represent it? 2. Right? Agree? 2 bits you need to represent it, right? To write the 3 in the binary, how many bits you need? 2. Right? So 0 0 0 1 1 1 1 0 1 1 1. Right? Right. So we can redefine addition and multiplication for this field in such a way that all properties of these operations are satisfied. So let's say in here. So 0 0, we put the elements in here and the elements in here. What's the identity for addition? 0 0. You add anything 0. Okay. What's the identity? What's the identity for multiplication?
0 1.
0 1. So we did the multiplication operation here. So is this a Galois field? Yes, because the number in here is a prime and there is an n positive integer numbers. We could represent this with how many bits? 2 bits. Clear? If we are using, for example, Galois field 2 to the power 8. How many bits we need to represent this? 8 bits, right? Okay, this is prime, this positive number, right? Positive number, integer, call it, right? Clear? Okay, so far we are going easy, right? So, a polynomial of a degree n minus 1 is an expression of the form, right? So, a polynomial of x. So, there's two parts for a polynomial, right? There is a coefficient and the x to the power something, right? So, in here, it's a0, x to the power 0. How much x to the power 0? 1. a1 to x to the power 1. Up to a minus 1, n minus 1 to x to the power n minus 1. Polynomial. That's how you write polynomials, right? Okay. Where x to the power I is called the ith term and ai is called coefficient of the ith term. There's terms and okay. Polynomial built of what? Terms separated by the plus sign, and each term has two parts: the coefficient and the variable, right? That's a polynomial, right? Okay. So if you look in here, for example, now what we are trying to do, how we can write binary value as a polynomial. Okay, so if I tell you I have this 1 0 1 0, how can I write it as a polynomial? Okay, so f of x equal, we start from here, it will 1 times x to the power 0, right? Right? Plus 0 times x to the power 1 plus 1 times x to the power 2 plus 0 times x to the power 3. This will go, this will go, so f of x equals x squared plus 1. So how can we represent a binary string as polynomial? Same thing we did in here, exactly what I did. So these are the strings. This is other in bits. I converted to polynomial, first reduction, second reduction, so I could write this as a polynomial this way. Clear so far? Good. Alright, to find the 8-bit word related to polynomial, now the reverse process. I need to convert this to bits. Easy or not easy? Easy. So how I do that? Okay, so 1, there is no 1, that means the coefficient was 0. The x, the coefficient was 1. The 2, the coefficient was 1, right? The 3, the coefficient was 0. The 4, 0. The 5 was 1. So I take 0, 1, 0 here, 1 here, 1 here, 0, 0, 1, 0, 0. So now I know how to convert both ways, from polynomial to bits, and okay, clear. Alright, so polynomials representing n-bit words using Galois F2 and okay, we already studied that. Okay. Alright. So let's talk about modulus. Okay. So for the sets of polynomials in GF2 to the power n, a group of polynomials of degree n, which is in here, is defined as the modulus. Such polynomials are referred to irreducible polynomials. Now, when you add polynomial to polynomial, the degree will be the same, right? Right? If you have the maximum x to the power 3 and you add, you know, but when you multiply, what will happen? It could be higher. So we have to reduce it. So what you have to do it modulus reducible polynomials. There's polynomials, you cannot reduce them, right? Examples. So this, for example, these two are, so this is the degree for degree 1, This is an example for a reducible polynomial. You cannot reduce this polynomial. So x plus 1 and x, you cannot reduce it. This you cannot reduce it. These are examples for polynomials that we cannot reduce. Okay? So whenever you have a polynomial higher than the degree you want, you have to reduce it. By what you're doing is the modulus. Okay? So let's take example. Okay. So for example, okay, so if we're gonna multiply this with this, how can you multiply this with this? So you're gonna take x5 and multiply it with all of these, right? You're gonna x2 multiply it with all of these, right? And then you take the x multiply it with all of these, right? You agree? That's how it is, right? So okay, so we use a simple, oh, this is what? This addition, I'm sorry, addition. So we convert it to the full. So we wrote this in here with the full. So because we are using in 2 8. So how many bits we have? 8 bits, right? So I convert, so where is the 1? 0. The x, 1. 2, 1. 3, 0. 4, 0. 5, 1. 6, 0. 7, 0. The same things for this. I put them in here and then I add them. So what will happen for addition, equal terms will cancel each other. So 0 and 1 will give you 1. 0 and 1 give you 1. 1 and 1 will give you 0. Like XOR, right? Okay? So when you add this to this, gave you this. Did we increase the level of the polynomial? No. We are to the power 8. This is to the power 5 within. So addition will not increase the power, right? Do you have to reduce for addition? You don't have to reduce. Whenever you add any two polynomials, it will remain within the same level, the maximum level, right? Where does the problem happen when you do multiplication? Okay? So in multiplication, what will happen that when you multiply x to power I by x to power j, what you're gonna do with the powers? You add them together. So let's take the same example. If you need to multiply this with this, what we'll do, you have to multiply the x5 with all of these terms, then add them. Multiply the x2 with all of this term, then add them, so on and so forth. So as you see here, x to power 5 from here, multiply it with this, the whole thing in here. You see it? We put it in here. You see it? Then x to the power 2, you see it here? We put it here. And again, we have multiplied with all of this. We put it here. And then x has to be multiplied. This is x. You see the x in here? We moved it here. And we have to multiply it with all of that, right? Then we have to multiply and add. Equal terms will cancel each other. So what we got at the end, when you do for the multiplication, we got x to the power 12. So how many bits to represent this polynomial? 12 bits. 12 bits. But we're working with 8 bits. So we have to reduce it. So to reduce it, what we do, we divide it by irreducible polynomials. One of the ones in the table. So to the degree, required degree. What's the required degree? Is 8. So you see, this is a reducible polynomial. Okay, so we took the modulus. The result with this irreducible gave you that power to x to the x power 5. Okay. So for addition, you don't have to reduce. For multiplication, you have to reduce if the power goes above what you need. Clear? Okay. So again, what we're trying to do here, we're trying to represent a stream of bits as polynomials. And vice versa, represent a polynomial as a stream of bits. What are the two operations we do? Addition. Whether you add bits or you add polynomials, you are okay. Okay, because you will be within the same level. Okay, but if you do multiplication, you will go above that. So you have to bring it back to the same level. How you do that? By doing a modulus with irreducible polynomial. Simple. Okay? All right. So, and that's what we did. All right. So how is reducible? How you do the reduction? By doing the modulus. So that's, for example, in here, We have this x to the power 12, x7, 18 here. And you divide it by the irreducible. What is the irreducible here? We put it here. And you do the division. So what is the remainder in the modules? That's the result. So you see the box in here? It's the one in here. Clear? Alright. Now, what other problems we have? How to calculate the inverse. How we calculate the inverse, multiplicative inverse? Last time, what do we use? Euclidean, extended Euclidean, right? Same thing in here. So in here, for example, if I have, this is in the field 4, 2 to the power 4. Find the inverse of this, modulus this. All I have to put, you know, the one of them in here and one of them here. And, you know, quotient and remainder and T1, T2. We already learned how to do that, right? We keep going until we have 1, 0. If we have 1, 0, that means what? That means there is multiplicative inverse. If there is no 1, 0 at the end, there is no multiplicative inverse, right? And what is a multiplicative inverse now? It's here. What is the difference? Before we were multiplying and dividing what? Digits. Now what we are doing? Polynomials. Polynomials. Okay? And that's a multiplicative inverse. We are able to find the multiplicative inverse, right? Same thing in here. This is Golos to the power 8. So I need to find the multiplicative inverse for this. All I have to do, okay, put this in here, put that in here, keep going until you get 1, 0, then this is a multiplicative inverse. You could try it by yourself. Okay? Alright. So multiplication using a computer. Now, you know, to multiply in a computer, usually you have to write a code for it. So what you do, so for example, if I need to multiply this by this, usually I multiply this by this. So the way to do it is, so we built like a database, like a table in the program. So what I have, x to the power 0 multiplied by polynomial 2. So x to the power 0, how much? 1 will give you the same polynomial, right? So x to the power 1 times the polynomial. What does it do? You multiply this with x. So you multiply this, you move it here with x, give you the result. Okay, then I have to reduce it. Now, to x to the power 2 equals to what? Equals to this multiplied with x. So I move this in here and multiply it with x. Very easy, right? You understand the point here? Right? So like I'm multiplying every time with a new x, right? So we start again. Let me repeat in here. So I need to, okay, what is polynomial 2? It's in here. X to the power 7, x to the power 4, x to the power 3. I put it where? Here. Then, usually I need to multiply it with one of the x's. X to the power 0, 1, 2, 3, 4, 5, up to 8. Up to 7. So, the x to the power 0 equals 1, it will equal polynomial 2. Now I need to multiply it with x. I move this in here, multiply it with x, gave me the x to the power 1 with polynomial 2. I multiply it with one more x, so I move this to here, multiply it with the x, and give me the result. I move this in here, multiply it with more x, and so on and so forth. So at the end, P1 times P2, it will give you that result. So in the computer, what you do, you keep multiplying with, okay, the results, okay? You could do it also as, you know, as binary. So you have polynomial 1, polynomial 2, okay? All right. So what you do, so this is, for example, x to the power 0 times polynomial 2 gives you polynomial 2, which is in here, okay? Then what you have, if the last one is 1, okay, you have to do, so you move this in here, this, okay, after the shift, left shift. So what is multiplying by x? What does it mean? Left shift 1 time, right? When I say 2 times 2, what I'm doing? Left shift, right? how you write 2? Okay, how you write 2? So for example, okay, let's say 2 is like this, right? Okay. 2, okay. So, yeah, it's like left shift, right? So this will 2 times 2 how much? 4. So okay, it will be 1 1 like this. Okay, it's like shift, right? So it's like left shift. So it will be 0 0 1. Left shift, right? That's a left shift, right? So in here, what we are doing in here, every time we are multiplying with extra x, we're doing what? A left shift. So in here, it ends with 1. Okay, so this what we have to do left shift, and we'll put it here. So multiplied by x. So that's the result in here. Okay, and we have to move it here after left shift. So it will left shift and 0 inserted, and this becoming like this, right? So every time move left shift, until gets to the result, right? So it's very easy to write a program code for it, right? So in here, for example, the addition table for GF. Okay, you have 3 elements. Okay, and so it could be represented as polynomials and all of that, right? And this is for the multiplication. Okay, all right. I'll stop right here. Okay, the class is over. Thank you.